Thank you for introduction. I'd like to give thanks, Professor Bear, for inviting me to give a talk here. I'm very happy to present here. Here is my hometown. Okay. Oops, wait a minute. Here is the outline of my talk. It consists of the 5 subsections. But first of all, in this talk, I'm going to introduce shift operators, maps, and then apply those maps on the non-Archimedean local rings, especially on the formal power series ring. And then I want to talk about my 2 main results as a kind of the application of the shift operators, especially. First of all, I'm going to characterize all continuous function on the formal power series ring in one variable t over finite field, and then its classical counterpart, which is p-adic integers in terms of the q or p-adic extensions of the shift operators, where it depending on the underlying the local ring, I'm going to use the q over p extensions of the shift of maps. As a second result, I'm going to provide the necessary and sufficient condition for the ergodicity of the one-Lipschitz functions on the defined over the formal power series ring of the binary field in terms of the digit. In this case, 2-adic digit shift operators. Okay, first of all, I'm going to introduce the shift maps in general. So a shift map is take place in the both the pure and the applied mathematics, even in the engineering, like the such as the computer science. So let me take 2 examples which comes from the dynamical system, because more or less my talk is related to the dynamical system. So you might notice this Gauss map G, which is closely related to the continuous fraction of the real numbers in the 1-unit interval. The map, Gauss map, is defined by that formula, 1 over x, fractional part of 1 over x if x is not equal to 0, otherwise g of x is 0. And then this is a very important function in the dynamical system, even it's related to the number theory. So another example is that the binary shift operators, which are defined on the 1-unit interval, the map on a t of x sends to the 2 times of x modulus 1. That means the fractional part of 2 times of x, where x is represented as the 2-adic form. So like that sum. So where the xi is just 1 over 2, 1 over 1, 0 over 1. And then it turns out that the 2 maps are left shift map on the sequence of numbers in the following sense. So S, the maps to the actually the x acts on the sequence of sequence of numbers like that. So S of x0 and x1, x2, and so on. This goes to the x1, x2, and x3. So that means just shift its components on the one element on the left. So in my case, I am interested in the shift operators on the formal power series ring in one variable of finite field of fq. So we have a nice representation of the x in this ring. I'm stick to this notation R as a formal power series ring. So x is written as the x0 plus x1 times 2 and so on. So S of x is defined by that formula. So x minus x0 divided by t. Then, so x1 times and so on, and then the x n times t to the n minus 1, where xi is just the elements in the finite field. So you can, the thing you can observe is that actually s operate as acts on the sequence of numbers like the left shift operators. And then you can iterate this operator many times. So nth iterative of the s is denoted by the s sub s up to the n, which is given by that formula. So x over x over the n is equal to x10 times the and so on. So now it is easily known that checked out that the s and the collection of the shift operators is continuous, and FQ linear functions on R, because FQ linear is really easy to check, but the thing is that the Sn is continuous. It follows the inequality for the valuation. So the valuation of v of t over S of n is equal to greater or equal to the valuation of x minus n. So when you think about the inequality, then the shift operator is continuous at x equals 0. Then by the linearity, and then that is continuous on everywhere on R. So, okay. Now we observe that this sequence of function is a continuous FQ linear functions. Okay. Here is the first my main result. Okay. So f is given continuous and FQ functions on the defined on R into K, and then we can consider the sequence of function in a polynomial ring in A. C0 is just f of 1, and Cn is f over t to the n minus t times f over t to the n minus 1, where n for the n equals or equal to 1. So the conclusion is that the first is the sequence of these numbers Cn turns out to be the null sequence. In other words, the t-adic valuation goes to 0 as n goes infinity, and then the infinite sum of the Cn times s to the n converges uniformly to f because of the part 1, because Cn is a null sequence, and then we can determine the assumed norm of the function f, which is given by the maximum of the absolute value of the C over n. Okay, and in this sense, we can simply speaking is that the collection of the shift operator is also normal basis for the FQ linear continuous function on R. So I'm stick to this notation. LCRK stands for the K Banach space for the FQ linear continuous function from R to K. Okay. So let me sketch the proof of this result. First of all, let me give you some well-known criterion for the also normal basis for the continuous function space of the local field. So, the cases we are interested in is 3 cases. First one is the linear continuous function space E. As I said, the FQ, double bracket T, and FQ, double parenthesis T. This is just the FQ linear continuous function space. And then there is another E, which is the continuous function space on the FQ, double bracket T. And then another E is just the classical, the analog of the E in the middle. So the continuous function space GP to QP. So here is the lemma 1 is a very well-known criterion for in this also normal basis. So let me state it. Okay, K is a local, field, and E is a K-Banach space, so that the double bracket of E is equal to the valuation group of K. That means whenever you take elements in E, you can scale the elements by the elements in the local field K. So we have a sequence of the function, or in my case, the function in E is we're going to say this is also null basis for the E, by which I mean that the sequence has satisfied the three conditions. First one is whenever you have a function E and it has a representation of in terms of f of n, and then the coefficients or null sequence, and then the norm of the function is determined by its coefficients. So here is the equivalent statement for the orthogonal basis for E. Is first one is every function f of n lies in the E naught, where E naught is just elements in the E whose the assumed norm is less than or equal to 1. The condition is that you can, because of the 1, actually you can reduce those functions denoted by f over n to the bar. They form a algebraic basis over the E bar. E bar is just E0 mod out m times E0, where f is a local field, the residual field of local field of K. So this is a well-known, very useful the criterion for the basis. And then as a corollary of this lemma, actually we can observe that this corollary, so Fn is a sequence of orthogonal basis of the E, and then we have another sequence, g of n, which is a sequence of functions in E such that the subnorm of the f of n minus g to the n is less than 1, strictly less than 1 for all non-negative integers. Then Gn is also the orthogonal basis for the space E. This is simply because of the two. The inequality gives you that the reduction of two polynomials are same for all n. That's why another collection of the functions in E, Gn is also normal basis. Okay, here is the here I can give you two. Two proofs, but one is based on the standard arguments in the non-Archimedean analysis. The other is based on the algebraic argument using the Serre criterion for the orthogonal basis for the continuous function space. The first of all, you can we know that f is continuous at x equals 0. So when you look at the construction of the sequence Cn, so Cn, Cn is t to the t over t to the n minus t times f over t to the n minus 1. So n goes infinity. That means t to the n equals to 0. So this function is continuous at 0. So Cn is obviously is a null sequence, and when n goes infinity, right? Because of a non-Archimedean metric. Okay, now so we know that Cn is a null sequence. Then the domain is compact. The series Cn, sum of the Cn s to the n converges uniformly to a continuous function. The thing we have to do is that you have to check out these two functions are same on R. So because of the f is my function is linear, and domain is compact. It's enough to check that these two functions are same at the monomial t to the n. So you just plug in the Cn, and then you have an infinite sum, but eventually the finite sum. But this sum is a telescoping sum, so that's why you cancel out, and then the resulting element is just the t to the n to t to the m. So I realized that after I proved this proof, this proof is reminiscent of the van der Pert's the arguments that a sequence of his function, is well known the orthonormal basis for the continuous function space on GP. So exactly the same thing is happened. Okay. Okay, now let me introduce another well-known, the basis for the linear FQ linear continuous function space. So first one is Gaussian linear, Gaussian FQ linear polynomials and Haas derivatives. So you might see this ENX. This is a well-known object in function field arithmetic, more or less relate to the Gauss, Gauss exponential function. This is just finite part of the Gauss exponential function. So ENX is just the product of the x minus alpha. Alpha runs through the polynomial whose degree is less than n. Okay, E0 is just identity x. And then Fn and Ln are just constant in A, well known. And then bracket n is just t to the q to the n minus n. Okay, so here is the Gauss FQ linear normalized the polynomial, which is given by the ENX divided by n to the divided by f to the n. Okay, this is normalized because of the known, assumed known. So there is another class of the non-polynomial, which is hyperdifferential operators or Haas derivative. It has many names, sometimes divided, more than 5. Yeah. Anyway, sometimes Haas, Schmidt, and the Teichmüller operators. So anyway, this acts on the polynomial ring very well. So here is the rule for the higher derivative. So you think about just the monomial t, dn over t to the m. In this case, t to the I. Then I choose n, binomial coefficient, and then t to the I minus n. Okay, this is okay, here is the well-known result. Actually, collection of normalized Gauss polynomial characterize the any continuous function, continuous FQ linear continuous functions. In other words, the f of x is written as that kind of sum. Whose the coefficient an goes to 0. More important thing is that this you can recover its coefficient an using the Gauss difference operators. This is a well-known operators. This operator is defined recursively like that formula. Okay, so now there is another result. A class of collection of the Haas derivatives characterize the FQ linear continuous functions. Also, we have cross formula for its coefficients using the iterating the formula, iterating Gauss operator of order 1. Delta means delta, Francis 1. Delta to the n is just iterate delta n times, and then it has a cross formula for the in terms of the function f. Okay. Okay. Now, so what's the relation in between any three bases? We have 3 sets of bases. One is the Gauss linear polynomial. Dn is Haas derivations. Sn is shift operators, right? So they are all equivalent. What I mean by that, if you know that one is orthogonal basis for the space, then the other is also orthogonal basis for the same space. Okay? So let me give you one example. There are inversion formula in between any two sets of bases and vice versa. For example, I'm going to show you the implication. 3 implies 1. So Gauss linear polynomial ENX has written as the in terms of a series in terms of the shift operators. So in this case, I put the a parenthesis n sub m as m's coefficients. By using the cross formula for the expansion coefficients, what I get is that this kind of a nice formula. So a n sub m is equal to, because simple the property of the Haas, the Gauss difference operators, the e n minus 1 to the q's power, and evaluate the t to the n minus 1. So simple the property of the Gauss linear polynomials, what I can observe that, I mean, these coefficients are a little bit simple to determine the evaluation. So n sub m is equal to 0 for m is less than n. If m and are same, then the a n sub m is 1. So a n m is divisible by t for m is greater than n. So this means that the sum norm of the difference of two operators is less than 1. So in other words, and then the Setter criterion implies the implications. All other implications are same because we have a closed formula for the expansion coefficients for the given basis. Okay. Okay. Now let's move on this expansion. Why we are interested in the linear orthonormal basis for the linear space? Simply because we have a nice result due to Cornet. He developed this principle, which is a kind of the common phenomenon in the function field arithmetic. So this principle says that any continuous, any orthonormal basis for the linear space LCRK can be extended to the orthonormal basis for the entire spaces via the Q-adic digit expansions. Okay, so to deal with this expansion, I have to define the definition. What Q digit expansion? So we have a sequence of a function b and x, which is orthonormal basis for the linear space LCRK, and then you just write non-negative integer j in the Q-adic form, a0 plus a1q up to the a to the s q to the s, and then where digits are in between the 0 and q, and then I'm going to set the bjx is defined by a product of the bn to the a to the n of x for n equal for the j equal greater than or equal to 1. b0 x is 1. And then there is another variant of the bjx, a kind of the twin brother, bj prime of x. This is prime is nothing to do with the derivative. Okay, that is defined by the that product. The product of the b an q to the n to the prime. Okay, so where b prime, an q to the n, a is just the digit of the q to the n is equal to, depending on the its digit. So digit a is equal to q minus 1, then you subtract 1 out of the bn to the a of x. Otherwise, you just raise a's power, use natural way. So now we say that this sequence is a Q-adic extension of bnx, okay, of okay. So as you see, the example of such a construction include the three classes. One is that the Gauss linear basis, and Gn is a Q-adic extension of the Gauss linear basis. Qj prime is a twin brother of Gj, and then this derivative. And then another class is a Haas derivation Dn, and then the bold dj is just the Q-adic extension of the Haas derivation, and dj prime is just the twin brother of dj, and third one is the Q-adic extension of the associated with the shift operators. Okay, and then let's move on the next things. In the case of the Galitz polynomial, this is well known due to Wagner, students of Galitz, Ghost, and Yang, a Chinese mathematician. And then this derivative, this is due to the Snyder and Conrad and myself. And then, so the same things happen for digit. I'm going to call the sequence of the Sj of x digit shift operator. Digit shift operator is also normal basis for this function space. Okay, now what is important is that I can recover its coefficients Cj in terms of the twin brother of the shift operators. So here is the result. The formula for the Cj. Cj is equal to -1 to the n times the sum of that kind of sum. Okay, this is true for the digit derivative. Also, this is true for the Galitz polynomials. Okay, the S prime just replaced by the digit derivative or the Galitz derivative. Okay, so this, here is the proof of the. I'm going to sketch of the proof because of the Conrad digit principle. It's enough to check that the map defined over there is isomorphism as a vector space. So here is the way we define. So you f of q, the bracket t, mod t to the n, goes to the n copies of the f of q. So f x goes to the has the vectors in the domain, each which has n components. The first component is just related to the zeroth iterate. The second component is related to the S1, and so on the S to the n minus 1. So if you know that the explicit representation of x, this map turns out to be just a shift map of x, representation of x. So, and then so we have to find out the coefficient formula, but I can give you a proof in 3 ways. The one easiest proof is to use the orthogonal formula that this sequence satisfies. Okay. Here is the. So I'm going to let the Bn, Bj, Bj prime be any of the the following 3 triples, Galitz, and this derivative and the shift operators. And then these all satisfy the binomial property. For example, Bj x plus u is a sum of that kind of binomial formula. This is also true for the Bj prime. Yeah, this is comes from the Lucas congruence theorem for the binomial coefficients in integer. The another property is that these 3 sets satisfies the so-called the orthogonality formula. So so the sum of the product of 2 the Bj alpha, Pk alpha, and the Bl prime alpha, summing over the monic polynomial or polynomial of degree less than n. So that value depending on the sum of the k plus l, which if k plus l is equal to q to the n minus 1, then the sum is minus 1 to the n, otherwise 0. So that's why this is called the orthogonality formula. Okay. Okay, what's happening to the classical case? So you have a shift map, not operators, on the periodic integers. So we have a periodic representation, and then as I did in the polynomial ring case, power series ring, you can define the shift operators the same way. So and S of n is just the nth iterate of the S, and then it is easily known that for the integers m and n, so S of n satisfy that congruence. So you know that the n is fixed, so m goes infinity. That means this operator is continuous at x equal x. Okay, so now, so when you have non-negative integer j, and you just write the periodically a0 plus up to the an to the p to the n, and then you form the periodic extension of the shift map S, okay, like that. And then this turns out to be the orthonormal basis for the continuous function space. Unfortunately, we cannot get the closed formula for the expanding coefficients, because this is a little bit complicated. But okay, I can give you two proofs. One is to use the coordinate principle, as I did in the polynomial, the power series ring case. Another proof is use the Mahler expansion for the shift operator or the n. So here is some nice result. S of n is a continuous function. That's why we have a representation in terms of the Mahler basis binomial coefficient x to the n, and then this sequence coefficient sequence possess the following property. So a parenthesis n j is equal to 0, j less than p to the n. A n j is equal to 1 for the j equal to p to the n. So more general case, I is bigger than or equal to 0, then j satisfies that inequality, then a n j is divisible by higher powers of p. So this lemma implies that you can figure out the zoom norm in difference between the Sn and the x choose p to the n. So that means the zoom norm of these two difference of two functions less than 1. So this implies that it's a periodic extension. Periodic extension of these two guys. I'm going to denote the by the s. First one sj, and the other one is Francis the x to the j. And then this, the two functions has that inequalities in zoom norm. So and then you use the Setter criterion, then they are equivalent. But using the coordinate principle, the x parenthesis j is defined this way. I'm sorry. I put x j is equal to the x p to the 0, alpha 0. I'm sorry, a0. I'm sorry. X p a1 x p to the s a to the s. This is a periodic extension over binomial coefficients x choose p to the n. The more or less the x Francis j is also equivalent to the Mahler basis. Okay. Sorry. Okay. This is the end of part 1. Okay. Now I'm going to introduce the another application of the shift operator to the non-Archimedean dynamical system. So recently I'm interested in this object. What I realized that actually this dynamics on the non-Archimedean space is closely related to the continuous function, the basis of the continuous function space. So, first of all, let me give you a definition of the non-Archimedean dynamical system, which is made of the three components. First, R is a measurable function. For example, p-adic integer or its analog in characters p. And then second component is just the measurable function. In this case, a continuous function. And then mu is just the normalized Haar measure on R such that the measure of the R is just equal to 1. This is a typical example of the probability measure on the p-adic settings. So you know that the mu of the a plus pi to the pi is just the uniformized in both cases, GP or it's analog in the function field. Suppose we have the a plus pi to the k, just the Klopen set, which generates a sigma algebra. So whose measure is given by its radius. So to speak, the 1 of the q to the k. So where q is just the size of the residue class field. So non-Archimedean dynamic system has many applications to the mathematical physics, computer science, and cryptography, and so on. Especially this, can be applied to generate pseudo-random numbers in cryptography. So I'm going to tell you what's the relation in between the non-Archimedean dynamic system and the function, the orthonormal basis for the continuous function space. So first of all, we have to understand the two terminology. Which one is one is measure preserving transformation or maps, or another one is the ergodic function on R. Okay, here is the definition. For function f is measure preserving on R if for every measurable function, a measurable set M in R, the inverse of M and M has have the same measure. Then we say that f is measure preserving. Okay, now the f is ergodic. We just say f is ergodic if it has no proper invariant subsets. In other words, any measurable subset M such that the inverse of M is itself M. This condition implies that measure of M is just 0 or 1. Okay, this is a definition for the measure preserving and ergodic functions. Okay, this is just the definition for the and then to begin with, actually we have to put the on the condition on f, which is one Lipschitz. So f should be one Lipschitz. This is an algebraic analytic terminology. In the algebraic terminology is compatible. So f is a one Lipschitz function if one of the following equivalent statements is satisfied. So look at the first condition. This is typically known in analysis for the one Lipschitz condition. So f of x minus f of y, the absolute value of the in this case, both cases, pi-adic valuation of f of x minus f of y is less than or equal to pi-adic valuation of x minus y. Okay. So in this case, the constant is 1. That's why we call this function is one Lipschitz. As well as the exponent is 1 also. And then 2 and 3 and 4, 5 are all equivalent. They are checked easily. But 6 is a kind of the algebraic definition for the one Lipschitz. So you have the x and y has, simply speaking, that f, the function preserve the congruence. In other words, x and y are congruent to each other modulus pi to the n, then their images are satisfy the same congruence. F of x congruent to f of y modulus pi to the n. Then one Lipschitz function induces reduced function on the quotient ring. So I'm going to this function by the f underbar f. So r mod pi to the n goes to itself. You know that this quotient ring is a finite set. So every one Lipschitz function induces for all n. This reduced function is just a function on the finite set to itself. Okay, here is the equivalent statement for the measure preserving and ergodic functions in terms of the its reduced functions. So one Lipschitz function f is measure preserving if and only if its reduced function is bijective for all n. Okay, this is due to the another criterion for the measure preservation is that the f is isometry. That means f preserve distance. So okay. Another equivalent statement for the ergodicity of function f. So a Lipschitz function f is ergodic if and only if its reduced function is a bijective and more condition, which is the transitive. That means that the orbit of this function is just 1. That means the image forms one cycle, only one cycle by repeating f. Okay. So the problem we have to work out here is that to characterize 3 types of the functions. First one is one Lipschitz and measure preserving ergodic functions on R in terms of expansion coefficients of f when f is written as infinite sum in terms of the well-known orthonormal basis. Okay, for the space CRK. Okay, here is I'm going to summarize the some known results for the ergodicity of the maps on the R. So we have the one Lipschitz function f written as the known basis, and then we have the following the characterization for the ergodicity on R. The first case in mid-1990s, Anasin established the ergodicity. He gave the necessary and sufficient condition for the ergodicity functions on the two-headed integers in terms of the Mahler basis. And then Anasin and the Kronikov and Yudova, they used the Van der Pop basis to give characterization result for the ergodicity in terms of the expansion of the Van der Pop basis. And then in what's happening to the function field anal situation. So Lin, Xu, and Yang, he proved that provided the same kind of the same analogous result for the function field case using the Van der Pop basis and the Galitz-Wegener basis. So now what I'm doing is that I'm going to provide the another basis for the ergodicity for the function under the binary field F2 using the digit derivative and the digit shift operators. Okay, here is the result for ergodicity for the one-list function in terms of the Galitz-Wegener basis. This is based on the useful criterion for the ergodicity in terms of the Van-der-Pelt basis. So this is the result. F of x is ergodic if the following the 5 conditions are satisfied. Okay. Now here is my result. Bi, Bn, Bn prime be any of the 3 triples. I mean digit derivative, Galitz polynomial, digit derivative, the digit shift operators, and then f of x is written as the any of the 3 bases. Then f is ergodic if and only if the same conditions on coefficients are satisfied. But the difference in between the Galitz polynomial and the digit derivative and the shift operators are one is a polynomial, the other 2 are just non-polynomial functions. That's why we have a little difficulty in dealing with the non-polynomial polynomials, non-polynomial functions. Okay. Here is the condition for the one-list sheets. Okay. So f of x is one-list whenever the following conditions are satisfied. I mean, this absolute value of Cn is less than the t to the integers part of log q to the n. Okay. Conversely, in the case of q equal 2, then these conditions are also necessary. But in general, we don't know yet this inequality is necessary. But for the Galitz polynomials only, these conditions are also necessary for any q. This is simply because of I'm dealing with the non-polynomial functions. Because when you look at the Lin et al.'s paper, actually they are using kind of the Newton type interpolation polynomial. So and then using their polynomial and then to compare the Galitz polynomial. That's how they prove this condition for the one-listness. Also, we have a condition for the measure preservation, and then use the two results, and then you can I can combine 2 results to derive the main result in the first slice. Okay. Okay. And now here is a sketch for the proof, but this is a kind of concise proof, actually sketch of proof. One direction is a little bit easy, but the other direction is a little bit involved with the computation. But the idea is that in the binary case, I mean the base field is the field of 2 elements, 0 and 1. So using the induction on the kind of the size of the n, and then using the Lucas congruence to derive the inequality for the coefficients. That's the idea, brief idea. And then I'm going to give you the simplest example with respect to the digit shifter operators. So according to my main result, actually this function gives you transitive functions for all the reduce the factoring. I mean, in this case, I just factor out the t to the 4. So we have 16 elements, right? So each element has 4 components, 4 bits. So I'm just select the initial value as the 1111. That means 1 plus t squared plus t cubed. You apply this function again and again, and then this sequence gives you 1 cycle. Okay, this is goes to the end up with the same element to begin with. Okay, so and then using this algebraic function, you can construct uniformly distributed sequence of a long period of any size. For example, 2 to the 80 is practical in the steam cipher. So anyway, I cannot show you the implementation of this sequence, but I have an implementation result of a transitive sequence of a period 2 to the 80. Okay. Here is I'm thinking some problems related to this talk. And okay, that's the end of my talk. Thank you.